understanding how one thing wins our attention compared to others. So you can think of walking in the street, and there are many things that you see. There's sounds, there's smells, and somehow only one thing penetrates your consciousness and you become aware of. Like if you walk on the street, your eyes see everything. They see trees and they see cars and they see houses, but somehow in your mind you focus on only one thing. Why is that? How does your brain decide that this information is going to be more dominant than anything else? There's some kind of competition occurring in your brain between all the images.
In daily life, we are always faced with competing stimuli, with competing distractions, and we eventually are thinking about one thing at a time. Now, how do we do that? This particular study was done in a group of neurosurgical patients undergoing brain surgery for severe intractable epilepsy that cannot be treated successfully with medications. And the key challenge in this patient is to identify an area in the brain where potentially the seizures are coming from, so that later this area can be resected in surgery with the high probability of cure. Now the way this is done is that the patient undergo implantation of specific electrodes that are placed in the brain in particular targets which are suspected to be the origin of the seizures. And they sit essentially on a ward in a hospital for several days awaiting a seizure to occur.
This is a very unique opportunity to be able to record not just the EEG, but actually the firing of individual nerve cells. We can listen in on the conversation that neurons have with each other. So we try to make the most of this incredible rare opportunity by asking the patient to play a simple video game in which they can use their thoughts to control what they see on a computer monitor in front of them.
We have seen in the past that there are particular brain cells which are able to represent information in a very abstract fashion, meaning that if you have got some stimulus in the environment impinging on the retina, by the time it comes to our nerve cells in the medial temporal lobe, it is encoded in an abstract fashion, meaning that if you are thinking now of Marilyn Monroe, that particular neuron in your brain and probably a group of other neurons like this particular neurons come to life with a particular memory or even the imagery of Marilyn Monroe.
And in this project, we wanted to see how speedily and selectively people can modulate the neural activity of these neurons in their own head. Moran Cerf developed a fancy feedback technique that allows him to visualize the firing activity of 4 more neurons in a patient's head using a movie. The way he does it is that he finds one neuron that responds selectively much more strongly, let's say, to Marilyn Monroe than to images of Josh Brolin. And he finds a second neuron that responds much more to Josh Brolin than to images of Marilyn Monroe.
We wanted to see how the patient in their own mind can really summon up one thought on the expense perhaps of another thought. And that was done in a way that the particular thought that they had could be depicted on a screen. So that the paradigm essentially starts with a fusion or a hybrid of 2 different concepts, let's say Marilyn Monroe and Josh Brolin. So you essentially start with a hybrid, and then by controlling your thought process, you can, in a sense, change the balance between those 2 representations. And now on the screen, you basically can very quickly learn how to bring in one image on the expense of another.
The stronger the Josh Brolin neuron fires, the more you see the image of Josh Brolin and the more the image of Marilyn Monroe will fade. So it's a competition. If the patient attends more to Marilyn Monroe, the Marilyn Monroe neurons will hopefully fire stronger and will be enhanced. Each movie is a unique function of the firing rate of these neurons. Each neuron really expresses how well, how quickly, how strongly patients can control their neurons using nothing but their thoughts in a conscious manner.
The patient would then, in his or her own mind, create a situation where those neurons responsible for Marilyn Monroe would essentially take over the neurons which are responsible for Josh Brolin. Meaning not only that the neurons of Marilyn Monroe would suddenly come to life actively, but those other neurons representing Josh Brolin would simply go down in their activity or essentially be inhibited.
Incidentally, this research also answers the questions of how do you suppress, how do you not think of a white elephant? Well, the answer is you do that by partially suppressing the responses of the neurons that encode the white elephant.
It's remarkable for the patients that they sit in bed and they didn't know anything about this thing. They didn't know that they can access their neurons a minute before we started, but now they get direct access to the neurons in their brain. They sit there and they're kind of fascinated by the ability to move things on the screen voluntarily, just by pure thought. So one of the remarkable results of the paper is that there are situations the patients actually see on the screen one thing, but are told to think of something else. So they see a picture of a spider on the screen almost entirely, but we told them your target is Marilyn Monroe, so think of her. And they're able to win the trial by thinking of Marilyn Monroe and overriding the visual input. So their eyes see a spider, but their mind thinks Marilyn Monroe. And those two concepts are kind of competing inside their brain. But because the mind is stronger than the vision, they're somehow able to override this vision and win the trial by making the picture of Marilyn Monroe appear on the screen. The environment offers a lot of information to us, and it's all kind of being read by our senses. We see things, we smell things, we listen to things, they're all getting to our brain. But we choose what to attend to.
So this, in a sense, brings the question is who is really in control? Do we control our neurons, or do our neurons control us? Well, of course, the solution may be that we ourselves are our own neurons, but that study essentially manifested our ability to override the sensory input by a voluntary process.
What our results clearly show is that at least in these structures, particularly in the hippocampus, in the parahippocampal cortex, thought overrides external realities. Here at least idealism trumps realism.
There may be in the future an ability to develop brain-machine interfaces which are based on human thought, on human intention, on human imagery, on human memory, or even on human dreams.